Okay, so 3.2, we're continuing to work with kind of some basic concepts having to do with vectors in n space, so in Rn we can call it. It's in this section that we're going to talk about the dot product, which we already introduced in our preliminaries video. But back then we only did it as an operation. We said, here's how you take the dot product of two ordered n tuples, or two vectors. We didn't give any interpretation geometrically to what a dot product was. And that's because we needed to do some of the development that we've done up until this point to make sense of that. But now we're ready to kind of venture into that territory. So before we get into dot products, we're going to talk about the norm of a vector. In section 3.1, I was referring to the length of a vector when it's measured by an arrow like this, or represented by an arrow. We were calling that the magnitude, because that's the typical terminology that you see in like physics or engineering. For us, though, we're going to stray away from using that terminology. We're going to be calling that the norm of the vector. So the norm is just a synonym for the magnitude. Now let's suppose that we have the components of a vector. We have it in component form. And for now, let's think about this vector as being in R2. How do you find the norm of a vector from its component form? How do you find a length? Well, again, remember, when you take a vector geometrically like this and represent its horizontal and vertical components as legs of a right triangle, that's exactly what this creates, a right triangle. I can use the Pythagorean theorem on this to figure out how long this vector is. So from the Pythagorean theorem, the norm of our vector squared would equal a1 squared plus a2 squared. Taking square roots, we say that the norm would be the square root of a1 squared plus a2 squared. Notice the notation that we're using. This is standard notation for the norm of a vector. It looks like a double absolute value. Okay, so that's what this means. It's the norm. And notice the norm is a scalar value, is a measure of length. So it's not a vector in its own right. We can also show, it's a slightly more complex argument, but it's typically one that's covered in Calculus 3. We could also show that if we're talking about a vector in 3 space, a1, a2, a3, that the length of that vector would be the square root of a1 squared plus a2 squared plus a3 squared. You also use a couple of instances of the Pythagorean theorem to prove that as well. But again, like I said, more complex argument. We're not really after that here. Notice the similarity. Really, the norm of either of these vectors can be thought of as the square root of the sum of the squares of its components. And so keeping that similarity in mind, it gives us a natural generalization of the concept of norm to a vector in n space. Even though we can't visualize the arrow that would notate, or that would resemble, that would represent a vector in n space, we can still talk about its length or its norm by simply generalizing this formula. The norm of a vector in n space is the square root of the sum of the squares of its components. So let's take an example. Here's a vector v in 4 space. I can't draw this, but I can find its norm. The norm of v is going to be the square root of the sum of the squares of its components, -2 squared plus -5 squared. That's the square root of 9 plus 4 plus 25, or root 38. Okay, so that would be the norm of that vector. A couple of really important properties of norms that are worth mentioning in a theorem. If you have some vector in Rn, and if k is any scalar, then the norm of a vector will always be non-negative, so greater than or equal to 0. The norm of the vector can only equal 0 if the vector is the 0 vector. So this is stated as an if and only if proof. The norm is equal to 0 if and only if the vector itself is equal to 0. And then finally, and these are all important, but this is an important one that we'll use in some proofs, the norm of a scalar times a vector is the same thing. It's equal to the absolute value of that scalar times the norm of the vector. So you can pull scalars out of this norm thing as long as you take their absolute value when they do come out. Okay? In 2-space or 3-space, all of these are relatively easy to picture. It's easy to see why these are true. But we want to prove this in a general way. So I'm just going to prove property B, and if you want, you can try the other two properties. Let's suppose V has as its component form V1 through Vn. This is an if and only if proof. So there's a couple of ways to prove if and only if proofs. You can prove them in both directions as different parts of your proof. So I can say if this is true, then this is true, and prove that. Then as a separate paragraph, say if this is true, then this is true, and prove that separately. What we're going to do here, though, is a method of proving an if and only if proof that you can't always use. If every step in your proof is reversible by itself, then you can put an if and only if between those. So here's an example of what I mean. We're going to start with this. The norm of V is equal to 0 if and only if the sum of the squares or the square root of the sum of the squares of the components of V is equal to 0. That's a matter of definition, which is why I'm justified putting the if and only if here. However, the radicand in this expression, so the sum of the squares, it's a sum of non-negative numbers, because the square of any real number is non-negative. And so to say that this is equal to 0 is the same thing as saying that each of these individual components is 0. Why is that the case? Well, if even just one of these squares here, if any one of these numbers that I'm adding was non-zero, it would be positive. And adding that to these other non-zero positive numbers. Sorry, I'm saying that the wrong way. Adding these to that positive number to these other non-negative numbers would result in a positive radicand, which means my square root would come out positive, not being 0. So that can only be true if and only if each of these, V1 through Vn, are equal to 0. But what does that mean if all of these components are equal to 0? Well, that can be the case if and only if V is the 0 vector. So every step of the way had an if and only if joining one step to the next, which means I don't have to do this in two different directions. Okay. Next up, we're going to talk about unit vectors. In math, the word unit means 1. So a unit vector is what we call a vector that has a norm of 1. And we use unit vectors for a lot of things, not just in this class, but in any class really where you're using vectors. They're extremely important. Calculus 3, we need to use unit vectors for lots of different things. And oftentimes, something that we want to do is take a vector v and determine a unit vector that has the same direction as v. So we can do that by multiplying v by a particular scalar that either shrinks or expands it to a vector that has the a size of 1 or a norm of 1. That can be done this way. If you multiply v by the reciprocal of its norm, this is a scalar times a vector, so we're talking about scalar multiplication here, that will always produce the unit vector that you're looking for. And I'm going to show you why down here, but just for notational purposes, even though we have no definition for the division of a vector by a scalar, we're going to use this notation, v over the norm of v, to really mean this. V is being multiplied by the reciprocal of that scalar. So why does this produce a unit vector? Well, let's take the norm of this vector and show that it's equal to 1. Because this is a scalar right here, the property that we talked about in that theorem a little while ago says that I can bring that scalar out of this norm as long as I take its absolute value. However, a property of norms is that they're non-negative. So the absolute value of this thing doesn't change it. I can remove the absolute value symbol and have no consequence to deal with. But now look at what I have. I have a scalar times a scalar, and they're reciprocals of each other. That product should come out to 1. Okay. When we do this, when we multiply a vector by 1 over its norm, that's called normalizing the vector v. Now, one thing I should point out here, notice this formula will not work if v is a 0 vector, because you can't divide by 0. Remember, this norm will equal 0 if and only if that vector is the 0 vector. But that's to be expected because you can't normalize the 0 vector. Anything I multiply to the 0 vector will still give me the 0 vector. I can never stretch it out to a length of 1. Okay, so let's do an example where we want to normalize a vector. This is a vector in 3 space, 3, negative 4, 2. The first thing I need to do is calculate the norm of that vector. So that's 3, negative 4, 2, which would equal the square root of 3 squared, which is 9, plus negative 4 squared, which is 16, plus 2 squared, which is 4. That's the square root of 29. Okay, now the normalized vector will then take the reciprocal of this and multiply this vector by that. So 1 over root 29 times 3, negative 4, 2. But that just gives me this, 3 over root 29, negative 4 over root 29, and 2 over root 29. And that's it. In this class, as well as if you've had Calculus 3, where you do this a lot, you'll notice that we don't bother rationalizing our denominators. There's no point in it, and it's just an extra unnecessary step. So we leave the root 29 in the denominators here. Okay. Now, having talked about unit vectors, there are some specific unit vectors in R2, R3, Rn that are so important that we assign them their own names and symbols. So they're what we call the standard unit vectors or standard basis vectors. And we'll talk about that term basis in chapter 4. In R2, we notate those vectors as I and j. And notice I is the vector 1, 0, j is the vector 0, 1. In R3, we call them I, j, and k. And you can see they're similar. I is 1, 0, 0, j is 0, 1, 0, k is 0, 0, 1. Once we get up into Rn, because we're being more general, we're not specifying exactly what n is, we stop using letters that are consecutive in the alphabet, because if n is big enough, we won't have enough letters. Instead, we call them E with a subscript, so E1, E2, all the way through En. And notice that each of these vectors is defined similarly. They have a 1 in whichever position the subscript matches. So in E2, you'll have a 1 in the second position here. Zeros everywhere else. Okay? All of these are unit vectors, and it's easy to see why. If you take the sum of the squares of the components in any one of these, it's going to be a sum of a bunch of zeros plus a 1. So the square root of that would still be a 1. These are all unit vectors. You will have encountered the ij or the ij and k, again, if you've had Calculus 3, or pretty much any engineering, physics, there's other sciences that use these. You will have seen these before. Usually in those classes, you see them with a little hat on top, something that looks like this. It's fine if you want to use that notation. We don't use it here just because we accomplish the same purpose by bolding them. So yeah, you're not going to see me calling it I hat, J hat, or anything like that, but that's a valid notation. Okay, what's the relevance of these vectors? Well, generally what we do with them is we take some arbitrary vector in Rn, and we try to decompose that vector into a linear combination of standard basis vectors. What does that mean? Well, let's work in R3. Notice if I were to take the components A1, A2, and A3 of this general vector in R3, I could start by writing it as a sum of these three vectors, A1, 0, 0, 0, A2, 0, 0, 0, A3. So splitting it up based on its components like this. Then I can pull each component out as a scalar, replacing it with a 1 inside that vector. You can reverse this scalar multiplication to see that it's the same thing as this. What's left in each of these vectors are exactly the vectors we defined up above, I, j, and k. So this is the vector a1i plus a2j plus a3k. Notice this, the scalars, we also call them coefficients. The coefficients on these vectors are exactly the components that I have up here, but I'm representing my vector not in component form, but as a linear combination of standard unit vectors. And there's reasons why we would want to do this, and we'll kind of encounter some of those later. Geometrically, think about what that represents. The vector I in R2 is the vector 1, 0. If you put that in standard position, its initial point is 0, 0. Its terminal point would be the point 1, 0. So it's going to be a vector of length 1 on the x-axis right here. If I scale that by a1, it's going to stretch that vector or compress it depending on what a1 is, but still keep me on the x-axis. Now if I do the same thing with j, the vector j, which again is the vector 0, 1, would be a vector that points towards the positive y-axis starting at the origin and has a length of 1. If I multiply that by a2, it's going to stretch that vector or compress it by that factor of a2. And then because I can move that vector anywhere I want and it's considered to be the same vector, I can stack it on the terminal point of a1i and think of the sum of those two vectors as like the legs of a right triangle. The hypotenuse of that right triangle with the initial point of the origin and the terminal point up here would then be the vector A that I decomposed into that linear combination. Okay, so we kind of think of those as coordinates in a sense. Similar case for vectors in R3. If I take the I, J, and K vectors, which point in the x, positive y, and positive z directions respectively, scale them all appropriately, and then add them up, it gives me this vector A here. Okay. All right. Let's go ahead and move on to the idea of distance. What do we mean when we talk about the distance between two vectors? Well, the way that we define distance intuitively is we say that if two vectors have the same initial point, then the distance between these two vectors is measured as the difference or the distance between their terminal points. So here, remember we did this diagram where we said that if two vectors have the same initial point, then the vector u minus v, that's u and that's v, kind of completes this little triangle right here. But notice the norm of this vector, the length of that vector, would be the distance between these two terminal points. And so we use that as a matter of definition. The distance between two vectors is defined to be the norm of their difference. Okay? So let's use that in an example. I want to find the distance between these two vectors in R4. So that means I'm looking at the difference between the two vectors. So 1, -3, -3, 0, 4, minus 3, -3, 2, 1 is equal to 1 minus 3 is -2. -3 minus -3 is 0. 0 minus 2 is -2. 4 minus 1 is 3. Okay, so the distance between those two vectors then would be the norm of this, their difference. I want the norm of -2, 0, -2, 3. That would be the square root of the sum of the squares of these components, which would be 4 plus 0, not going to write that, plus 4 plus 9. 8 plus 9 is 17, so that's going to be the square root of 17. Okay, that's the distance between those two vectors. All right. Now, here we start to get into the dot product, which again we've already defined, but here's that definition again. If you have two vectors, u and v in Rn, we define the dot product of those two vectors to be the sum of the products of their corresponding components, u1 times v1, u2 times v2, and so on, adding all of those up. Again, remember the dot product, even though it's taking a product of two vectors, comes out as a scalar. It does not come out as another vector. Okay? The dot product has a number of very interesting properties. The first one that we're going to look at is what happens if you take a dot product of a vector with itself. So let's suppose, again, u is this guy, u1 through un. If you take the dot product of u with itself, then the first part of this sum is going to look like u1 times u1, or u1 squared. And that's what the entire sum will end up looking like, u1 squared plus u2 squared, and so on. This is the radicand that appears when I want to find the norm of u. Because what does the norm of u look like? The square root of this. So if I were to take the square root of this dot product, which is the same as the square root of this sum of squares here, I get the norm of u. So there's a direct relationship between the dot product and the norm of a vector. The norm of u is equal to the square root of the dot product of u with itself. Okay? Okay, let's go ahead and move on to a theorem here. Let's see. So these are some properties of dot products. Dot products have what's called the symmetry property. Alternatively, we can call it commutativity. We proved this, if you remember, back in that preliminaries section. They also have the distributive property. The dot product of a vector will distribute from the left over a sum of two vectors. We have something called the homogeneity property. I've used that term previously in this class, but what it refers to is if you have a scalar times a dot product of two vectors, you can multiply that scalar to the first vector and then take the product of that with the second vector. This was copied from the book, and there's a little bit of a typo here. That k should not be bolded because it's not a vector, it's a scalar. So just be careful with that. And then property D here. If you take a dot product of v with itself, it will always be greater than or equal to 0. And the dot product of v with itself will equal 0 if and only if v is the 0 vector. We'll prove D, but we've actually kind of already done that because this is very similar to the proof that we've done previously. If you let v be a vector in Rn, then what is the dot product of v with itself? Well, what we just showed is that it would be the norm of v squared. The norm is already a non-negative number. Squaring it is still going to keep it a non-negative number, so that would make it greater than or equal to 0 automatically. Now, we know that the dot product of v with itself can only equal 0 if the norm of v is equal to 0, because, again, we have this connection between those two things. But we've proven a theorem that says the norm of v is 0 if and only if v is the 0 vector. So there's kind of nothing to prove there. It's just sort of restating things we already know. Okay, that's all the time for this video. We'll pick up where we left off in the next one.